This is applied physics course for undergraduate students, and today we will talk about the chapter 8, rotational kinematics, and this is part 2 of rotational kinematics. I am Dr. Nasir Mirza, and I will be discussing the rotational kinematics, its second part. We have already gone through this, the relationship between linear and angular variables. Whenever there is a rotation, for example, a rigid body such as a merry-go-round rotates around an axis, each particle in the body moves in its own circle around the axis. Since the body is rigid, all the particles make one revolution in the same amount of time, that is, they have the same angular speed. However, farther particles away from the axis have greater circumference of the circle, so the faster their linear speed is. You can notice that on a merry-go-round, you turn with the same angular speed regardless of your distance from the center. But your linear speed increases noticeably if you move to the outer side of the edge of the merry-go-round. So we often need to relate the linear variables such as the displacement S, the velocity V, and acceleration A for a particular point in rotating body to the angular variables such as the angular displacement theta, angular speed or angular velocity omega, and angular acceleration alpha for the body. The two set of variables are related by r, the radius of the rotating object, which is a perpendicular distance of the point from the rotating axis. Let us first consider the position for a rigid body. If a reference line is given on a rigid body rotating through an angle theta, then a point within the body at a position r from the rotating axis will move a distance s along a circular arc, and s will be equal to r into theta. So angle must have been measured in the radians because it is the definition of angular displacement, that is, the angular measures are in the radian. So displacement variable is related to the angular displacement through this S is equal to R into theta. For the speed, we differentiate the last equation with respect to time, and R, the radius is kept constant, then it leads to ds over dt equal to d phi over dt, the angular displacement's rate of change, multiplied by r. And the angular displacement is basically the speed, the angular speed of the rotating body, and ds over dt is the tangential linear speed of the point in question. Therefore, the tangential speed is related to the angular speed multiplied by r. So we say linear velocity is always tangent to the circular path for the point in question when it is rotating. And the above equation is telling us that all the points within the rigid body have the same angular speed, then the point with the greater radius will have the greater linear speed or the tangential velocity. If we further differentiate this relationship with respect to time, we will again have r held constant, then dvt over dt is equal to d omega over dt times r, and dv over dt represents only the part of the linear acceleration that is responsible for the change of the magnitude of the velocity, that is for the linear velocity, which is tangential velocity. And uh, likewise, the part that is linear acceleration is the tangent to the path of the point in question. So we call this the tangential component of the linear acceleration for the point, and we write a tangential equal to the alpha, the angular acceleration multiplied by r. So the angular acceleration is related to the linear acceleration or the tangential acceleration through these this relationship. A particle or a point, when it is moving in a circular path, has a radial component of the linear acceleration, and that radial part is always directed towards the center, and it is the AR equal to the velocity square divided by r, and here the velocity is again the tangential component of the velocity. So this acceleration is always a radial component, or sometimes known as the centripetal component, because it is directed towards the center. And it can also have the tangential component, the acceleration. This component and the linear acceleration is directly radially inward, and it is direct responsible for the change in the direction of the linear velocity. So if we substitute v for the relationship we have already derived for the angular acceleration, then that is the v is equal to the angular velocity multiplied by the r. Then we get the radial component of the acceleration equal to omega squared times r. The resultant acceleration or the total acceleration of the point is the vector sum of these two components of the acceleration, the radial component of the acceleration plus the tangential component of the acceleration. Let us do this example starting from rest at time t is equal to 0. A grindstone has a constant angular acceleration of 3.2 radians per second square, and the angular velocity is 8.6 radians per second. If the radius of the grindstone is 0.24 meters, calculate the linear or the tangential speed of the point on rim, and the tangential acceleration of the point on rim, and the radial acceleration of a point on the rim at the end of 2.7 seconds. So we know from this question that the constant angular acceleration is given, alpha is given as 3.2 radians per second square. The angular velocity is given as omega equal to 8.6 radians per second. The radius of this grindstone is given 0.24 meters. So we can calculate the velocity, the tangential velocity equal to omega times r, and we know omega and r, so we get 2.1 meters per second, the velocity. Similarly, the tangential acceleration is alpha times r, so alpha is 3.2 radians per second square, and r is 0.24 meters. Therefore, the tangential acceleration is 0.77 meters per second square. The radial component of the acceleration or the centripetal acceleration is given as omega square times r, Since we know the omega as 8.6 radians per second, so we square it and multiply it with 0.24 meters, and the answer is 18 meters per second square. So the centripetal acceleration is the largest acceleration value, and the tangential component is small. Before we do a problem for a pulsar, let us briefly talk about a pulsar. Pulsar is a star. It comes from the pulsating radio source, which is a highly magnetized rotating neutron star. A neutron star is basically full of neutrons. So its size is small, its size is compact, and its mass is very large. It emits beams of electromagnetic radiation out of its magnetic poles. So these radiations can be observed only when the beam of the emitted light points towards the Earth. And since it is rotating, it behaves just like a lighthouse. A light beam comes and is thrown on Earth, and then it goes away, and then the next round, another beam comes and then goes away. So it is responsible for the pulsed appearance of emissions, and the neutron stars are very, very dense materials and have very short and very regular rotating periods. In fact, their rotating periods are used for synchronization of clocks. Let's see what we have been given here with the animation in the Wikimedia. So if I can show you this, we are sharing this rotating object, and it's let me let me slow down the playback speed and show you. As you can see, the beam, the red colored beam is pointing out, and at the center we have a source, the neutron star. The neutron star is rotating, and its magnetic field is also rotating. The beam which is coming out from the poles is searching sort of a lighthouse beam. So that's a neutron star simulation. Let's go back to the lecture and see one example on a pulsar. A pulsar, which is rapidly rotating neutron star, is rotating, and it has the rotational period of t equal to 0.033 seconds. The radius of the star is given as 15 kilometers. We know very well that the density of this star is very, very high, a large value. The question is, what is the tangential speed at the point on its equator? The rotational speed has been asked. So first we see what is given. We are given with the period t equal to 0.033 seconds, the radius r equal to 15 kilometers, and the angular velocity omega equal to 2 pi radians in completion of one circle divided by the period, which is the time required to complete one circle. So we get the answer as 190 radians. Once we know the angular speed, now we can find out the velocity. The tangential speed is the vt equal to omega times r. 190 radians per second multiplied by the r, which is 15 kilometers, 15 multiplied by 10 to the power 3 meters. So we get the answer 2.9 into 10 to the power 6 meters per second. We know very well that the speed of light is 3 into 10 to the power 8 meters per second. And if I divide this velocity, Vt, by c, I get about 1 into 10 to the power minus 2, which means that it is about 1% of the speed of light. So very high speed. In fact, the rotating star has very high speed, and it is at a very large distance away from Earth, and still its beam is always knocking at the uh, Earth with such a high rotational motion. Let's look into this example in which we are seeking the relationship between the linear and the angular variables. And we would like to describe that this chimney, which was a rigid body, when it was ruptured, how this process happened. On a rotating body, the points that have different distances from the axes do not have the same linear displacement, they do not have the same speed, they do not have the same acceleration. But all the points on a rigid body, which is rotating about a fixed axis, do have same angular displacement, same angular speed, same angular acceleration at any instant of time. So when a tall chimney is toppled by the explosions, the explosive charges that are allowed to happen at the base, it will often break as it falls. The rupture starts on the downward side of the falling chimney. Now let's see how this goes. Before the rupture, the chimney is a rigid body, so it will rotate about its axis near the base with a certain angular acceleration alpha. At the top of the chimney, it has a tangential acceleration, A tangential. Now the vertical component of this A tangential can easily exceed the gravity. So the top of the chimney is falling with a vertical acceleration which is greater than the value of g. This can happen only as long as the chimney remains a single rigid body. So there will be a shear force which will be more than the mortar can tolerate. So when chimney is falling down, its rotation will cause it to break uh, from the positions that are closer to the base. Such cases do also occur when we are studying the uh, injury which is caused to the leg and the connected foot. And once the rotating foot has a constant or the same angular displacement and same angular speed, the bone which is attached to it, the leg bone, will have different uh, linear displacement and speed and the acceleration at different positions as a function of the distance from the axis of rotation. And therefore, a rupture or injury can happen to the bone and the foot connected. Let us do one more example of a compact disk The audio information is generally stored in series of pits and the flat areas on the surface of the disk. The information is often stored digitally, and alternations between the pits and the flat areas on the surface represent binary ones and zeros, and they are read by the compact disc player and are converted back to the sound waves. The pits and the flat areas are detected by the system, which consists of lasers and lenses. So the length of the strings of ones and zeros representing one piece of information is same everywhere on the disk, whether the information is near the center of the disk or near the outer edges. So in order to the length of ones and zeros always passes by the laser lens system in the same time period, the tangential speed of the disk surface at the location of the lenses must remain constant. Then the angular speed vary as the laser and lens systems move radially along the disk. So in a typical disk player, the constant speed of the surface at the point of the laser lens system is equal to 1.3 meters per second. Let us do an example to illustrate this. Find the angular speed of the disk in revolutions per minute, RPM, when the information is being read from the innermost first track at the radius r is equal to 23 millimeter, and the outermost final track r is equal to 58 millimeters. Part B is to find the maximum playing time of the standard music CD is 74 minutes and 33 seconds. How many revolutions does the disk make during that time? So let's do the first part. We can find the angular speed that will give us the required tangential speed at the position of the inner tracks. The omega I, the initial speed, is velocity divided by the r. Now, if r is equal to the 23 millimeters, then the velocity is 1.3 divided by 2.3 into 10 to the power minus 2 meters. So millimeters have been converted, and we get the answer as 57 radians per second. We can convert the radians into the revolutions, one revolution per 2 pi radians, and the 60 seconds are there in a minute. Therefore, the answer is 5.4 into 10 to the power 2 revolutions per minute. For the outermost track, the velocity divided by the r, which is 58 millimeters, we get 2.1 into 10 to the power 2 revolutions per minute. Now we can see that the angular speed of the outer track is small and the inner track is large. To keep the velocity constant, the player adjusts the angular speed of the disk so that the information moves past the object lenses at a constant rate or constant velocity. Now we know that the angular speed is always decreasing, so we assume that the decreasing happens steadily with the alpha equal to constant. The alpha is the angular acceleration. If at time t is equal to 0, the disk begins with the angular speed of 57 radians, then the total time t is 70 into 60 plus 33 seconds, and the answer comes to be 4,473 seconds. The angular displacement theta, d theta, during this time interval is theta final minus theta initial, and this is given by the omega initial plus omega final divided by 2 multiplied by the time. And we substitute these values and reach at the result of 1.8 into 10 to the power 5 radians. So the total revolutions are 1.8 into 10 to the power 5 radians multiplied by 1 revolution per 2 pi radians. So answer is 2.8 into 10 to the power 4 revolutions. What total length of the track moves past the object lenses during this time? Because we know that the linear velocity is constant and the time interval is then very straightforwardly calculated as xf equal to velocity multiplied by time. 1.3 meters per second is the velocity. Total time taken is 4,473 seconds. So the track length is 5.8 into 10 to the power 3 meters, and this is kilometer. So 5.8 kilometers is the total track length that has been covered during this time. Then there is a question that a CD is used, then what is the angular acceleration of the CD over 4,473 seconds time interval? Assume alpha to be the constant. So direct approach to solve this problem is to use the result of the part 1. We obtained a negative number of angular acceleration because the disk spins more and more slowly in the positive direction as the time goes on. Our answer should be relatively small because it takes a longer time and more than an hour. So for the change in the angular speed to be accomplished, we see that from V final, we reach at V final from V initial in this time interval, then this is 7.8 into 10 to the power minus 3 radians per second square. So a disk experiences a gradual decrease in its rotating rate as we expect because its angular velocity is reducing from 57 meters radians per second to 22 radians per second. In the end, we would like to connect the relations of the angular velocity and the angular acceleration to vectors form the spatial relationship between the angular vector omega and the angular uh, acceleration alpha and the linear vectors velocity v and the acceleration a we can write in the compact form using the vector cross product. The vector cross product of two vectors a and b is a c vector which we can write as c equal to a cross b. Such a vector has two properties that are really important. The first property is the magnitude of C is equal to AB sine theta, where A is the magnitude of vector A and B is the magnitude of vector B. Here we have shown vectors in the bold letters and the magnitude in the normal letters. Theta is the angle between the vector A and B. Vector C is perpendicular to the plane, which is formulated by A and B. So wherever there are A and B, that plane has a perpendicular, and the vector C is on the direction of that perpendicular. Its direction is always determined by the right-hand rule, which says we go from A to B. As we go from A to B, our right hand fingers are going to point in the direction of rotation, and then the pointed thumb will be showing the direction of the vector C. So if we look at this picture, a particular point in a rotating rigid body, for example, P point, here is the P point. It is located at R vector from its origin, and the R sine theta is on that perpendicular plane. So the particle has an angular velocity omega, which is shown here as red colored vector, and the tangential velocity is v, which is shown here. So the magnitude and the direction of the cross product omega into r. Omega into r is identical to the, if we go from omega to r, we get a perpendicular to this plane, a vector which is velocity vector v. So velocity is omega cross r vector. Figure shows this, figure shows that a point P has an angular acceleration along the z-axis, as you can see, alpha, and r vector is shown here. The particular particle also has a tangential acceleration, which is shown here as a tangent to this circle, and AR, which is the radially going inward vector, and this is acceleration, radial acceleration. So we can find the acceleration by taking derivative of this above equation, v equal to omega time cross r. Let us do this, but we must preserve the order of the vectors when we are taking the derivative. So acceleration is equal to d over dt of omega cross r. And I open this, then I take the omega as here with the product, and then I take the derivative of r first. So dr over dt is shown. In the second term, I take the derivative of omega first, d omega over dt, and then take the cross product with r. Note that both terms have on the right of the equation omega, and r comes afterwards. So omega always comes before r. Omega always comes before r. So we have preserved the order in which these vectors are occurring, because we know very well that omega cross r is not equal to r cross omega. So order is important. Let us do now find out what are these things. The acceleration A is basically the derivative of v with respect to the time. The vectors alpha is d omega over dt. If I take the derivative of omega with respect to time, it is the angular acceleration. So this term is angular acceleration. And dr over dt is actually, dr over dt is actually velocity. So making these substitutions, we get the acceleration, total acceleration as omega cross v plus alpha times r. Omega is the angular acceleration, angular velocity, and v is the tangential velocity. Alpha is the angular acceleration, and r is conventionally the radius for the point P. According to the rule for finding the magnitude of the cross product, the magnitude of alpha cross r can be said as alpha times r times sine of theta. And if the angle between the alpha and r is 90 degrees, then this alpha into r, because sine of 90 degrees will become 1. So also we know that the direction of alpha cross r is same as the tangential acceleration direction. Therefore, this term alpha into r is acceleration, tangential acceleration. The magnitude of the vector cross product in the other term, which is omega cross v of the equation, we can see that this is omega into v because angle between these two vectors is 90 degrees. So we can also write omega into the velocity, the tangential velocity, equal to omega square into r because the tangential velocity is given as omega into r. So the radial acceleration term we are getting. The right-hand rule for the vectors product of omega cross v shows that it points radially inward, and therefore this omega square r, which is the radial acceleration, it is pointing towards the center. So it is a centripetal acceleration. So the product omega cross v has the magnitude and the direction of the radial acceleration. Therefore, we write this term as a radial acceleration equal to omega cross v. Making these two substitutions, the first substitution was the angular acceleration cross product with r is the tangential acceleration, and the above term, the radial acceleration, is equal to omega cross v. Therefore, our equation of total acceleration is equal to omega cross v plus alpha cross r, and both are the radial and the tangential component of the acceleration. So this equation gives us the vector representation or a vector relationship between the angular and the linear acceleration. Previously, we got a relationship between the angular velocity and the tangential velocity and its vector form. So with this, we have the vectors for omega and vectors for alpha and their relationship with the uh, linear terms such as the velocity and acceleration. We stop here, and in next lecture, we will discuss the rotational dynamics, having taught the inertial things of rotation or the rotating bodies. And we will also try to correlate when we have a rotational motion. Under the rotational motion, when there are forces and when there are torques, how the Newton's law is modified. We stop here and wait for the next lecture. Thank you so much.